Hi, my name is Ming-Chieh. Here I'm going to discuss our work, Falsification of Internal and External Validity in Observational Studies via Conditional Moment Restrictions. We will start from our motivation. Normally, when we're interested in the treatment effect of interventions or policies, the golden standard is considered to be the randomized controlled trial. This is because randomization process would remove confounding, which would lead to unbiased treatment effect estimates. In other words, randomization ensures internal validity within the RCT. However, randomized controlled trials often have strict inclusion criteria, which limits their external validity. So often we do not have the ability to generalize their causal effect estimates across wider populations. In addition, the sample sizes of randomized controlled trials are often small. So apart from average treatment effects, we often do not have power to infer conditional average treatment effects or personalized treatment effects. In contrast to RCTs, observational studies often have a broader and more diverse population, and they often have larger sample sizes. That is, we have more power to infer on the conditional average treatment effects or personalized treatment effects. However, because the treatments in observational studies are not randomized, there may be potential unobserved confounding within these studies. In fact, in practice, there is widespread skepticism toward both the internal and external validity of observational studies, so that their use in evidence generation is very limited. Therefore, our goal is to use experimental data, which is RCT data, as a form of validation so that we can falsify assumptions of external and internal validity in observational studies. That is, if we have an observational study that passes the falsification process, then we will be more confident that it may not be biased. To elaborate, suppose that we have one observational study and one RCT. The observational study is depicted in the left. With this study, we can produce treatment effect estimate with respect to the RCT population, which is shown in the middle. Now, since we also have an RCT data, we can produce another set of treatment effect estimates with respect to the RCT population using the RCT data. Now we have two different sets of estimates, and under the assumption of internal validity and external validity of observational studies, these two sets of estimates should be estimating the same thing, so they should be comparable. Therefore, we can leverage on this fact and test the equality of these estimates to serve as a test of internal and external validity assumptions of observational studies. There are a few desired properties of our falsification test or falsification algorithm. First, we want high power. That is, when either the internal validity assumption or external validity assumption is violated by the observational study, we want high probability that we reject the observational study. Second, we want controlled type 1 error. That is, when both the internal and external validity assumptions are met, then we want the rejection rate for the observational study to be controlled at a nominal level, for example, 0.05. Third, we want an explanation of falsification. That is, if we can know, like when the observational study is rejected, that the causal effect estimates from the observational study tend to be positively biased compared to RCT for older and male patients. That would be very informative because now we can look into this subpopulation and look for the reason for the bias. Our contribution here is that we showed how assumptions of external and internal validity can be converted into a set of conditional moment restrictions, which can be tested using existing techniques with theoretical guarantees. To put our study into context, we will talk about a few prior approaches to the falsification procedure. One approach is to directly compare the average treatment effect of observational studies and RCT after transportation. The caveat of this approach is that it can lead to false negatives. For example, suppose that males have positive bias for the observational study and females have negative bias in the observational study. then if we only test for ATE, then we may not be able to detect the differences between the conditional average treatment effect. Also, because we only look at ATE and do not look into subgroups, we do not have any explanation for the rejection. There is also another approach which divides the population into subgroups and compare the group average treatment effects of these populations, so that if any one of the population have different group average treatment effects between the observational study and RCT, we can falsify the observational study. However, because we divided the population into several groups, we need to correct for multiple hypothesis testing in this approach, which loses power. Also, we need a priori specification of the subgroups, and it would be nice to find these automatically and efficiently. Before we delve into the falsification procedure, we will formalize some of the assumptions we make along the way. The first set of assumptions is very intuitive, which is the internal validity of RCTs. Because the treatment assignment is following a randomization process in RCTs, we have ignorability of the treatment assignment, and we have fixed probability of assignment. In addition, we assume that there is consistency, which means that the observed outcome actually corresponds to the counterfactual outcomes. One set of assumptions we would like to test is the internal validity of observational studies. The internal validity of observational studies can be split into three different assumptions. The first one is conditional ignorability, which states that given the observed covariates, the treatment assignment is actually ignorable. And for the last assumption, the positivity assumption, it means that for every type of patients, there is a non-zero probability of this patient being assigned to one intervention or another. And for the consistency assumption, this is very similar to the previous assumption we set in the RCT. However, internal validity is not enough for the observational study, since we still need to be able to compare causal effects between observational studies and the RCT. So we need the external validity assumption, which can be split into two different assumptions. The first one is mean exchangeability of contrast, or exchangeability of conditional average treatment effects. The definition of conditional average treatment effect is the conditional expectation of the difference of counterfactual outcomes under treatment versus under control. Therefore, because conditional average treatment effect is exchangeable between the studies, we have the following mathematical expression where S here is the indicator variable for RCT or observational study. The second assumption for external validity of observational study is the positivity of selection. This means that if a type of patient has a non-zero probability of being in the RCT, then it should still have a non-zero probability of being in the observational study. This ensures that we can use the transportability formula to transport the treatment effect estimate from the observational study to the RCT population. A side note is that here we're making the assumption of mean exchangeability of contrast. And this assumption is actually weaker than the standard assumption of exchangeability or transportability of counterfactual means. Please see our paper for empirical and theoretical motivations for this assumption. And we also provide examples for when counterfactual means in the RCT are not identifiable from the observational study, but the causal contrast is actually identified. Now we can get into our falsification procedure. With the assumption of internal validity of RCT and both internal and external validity of observational study, we can construct a set of unbiased instance-wise conditional average treatment effect signals from the observational study and the RCT. For the observational study, we use psi1, and for the RCT, we use psi0. Now, because psi1 and psi0 all estimate the same conditional average treatment effect, so we have the conditional expectation of psi1 minus psi0 should be 0. This is the set of conditional moment restrictions we are using in our test. To look a bit further, we want to know how we can construct psi1 and psi0. Psi 0, which is from the RCT, is constructed using a IPW, which is inverse probability weighting style estimator. Under the internal validity of RCT, it is an unbiased estimator for the conditional average treatment effect in the RCT population. And for Psi 1, which is the estimator from the observational study, we use doubly robust transported estimator to account for the high dimensional covariance. Under the assumption of internal and external validity of the observational study, Psi 1 is also an unbiased estimator for the conditional average treatment effect in RCT population. Therefore, as we have said, if we let psi equal psi 1 minus psi 0, then this instance-wise signal psi should have a conditional expectation of 0 px almost. We have now translated our null hypothesis, which is the internal and external validity assumptions for the observational studies, into a set of conditional moment restrictions. Now, by the law of iterated expectations, for any measurable function x, we have the expectation of psi f of x is equal to 0. Actually, if we use a previous result from 1det and constrain the function f to be within an RKHS with integrally strictly positive definite kernel, we can ensure that the set of conditional moment restrictions above is actually equivalent to the marginal moment restrictions below. To test for the set of marginal moment restrictions, we can find f within the RKHS that maximizes the square of the expectation of psi f of x. If this statistic is away from 0 significantly, then we reject the null hypothesis, meaning that we want to reject the observational study. Notice that when we're constructing the statistics, we're trying to maximize the square of the expectation of phi f of x. This means that if psi has a large magnitude and is positive, then f of x should be positive. When psi has a large magnitude and is negative, then f of x tends to be negative. In other words, this test statistic is trying to find regions in X where the difference in K estimates between the observational study and RCT, which is reflected by psi, is large. Therefore, we can find the maximizer f star, which we call the witness function, and visualize it to introspect regions where the bias is the largest. We now introduce our semi-synthetic experiments using the IHDP dataset. For the covariates, we adapted it from the Infant Health and Development Program dataset. For the observational studies, we simulated the covariates and introduced a difference in covariate distributions between the observational study and RCT so that transportation is necessary. For the outcomes, we simulated the outcomes using the setting of our previous work. To introduce confounding in the observational studies, in some analyses, we concealed some of the confounders. We compared 3 different approaches for the falsification procedure. The first approach, MMR contrast, is our current approach. The second approach, GATE, is comparing the group average treatment effect between the observational study and the RCT among different pre-specified groups. The third approach, ATE, is comparing the average treatment effect estimate between the observational study and the RCT after transportation. As we can see, when there is no confounding in the observational studies, all 3 approaches largely retain the nominal level of 0.05, which is the significance level of reset. However, when there is bias in the observational study, our method, which is MMR contrast, shows superior power, particularly when confounding strength is lower, which is shown in the upper panel. In addition, we visualize the change in witness function f star for pairs of covariates in this semi-synthetic experiment. In the left panel, we can see that f is largest when the mother drinks and the birth order is small. And for the right panel, we can see that irrelevant of whether the mother drinks, as long as the neonatal health index for the infant is low, then we have a large bias. Finally, we introduce a real-world data experience using the WHI dataset. The data is adapted from the Women's Health Initiative dataset, and for the violation of validity assumptions in observational study, we engineered selection bias within the observational dataset. The results show that our methods has superior power when selection bias was introduced. For more results and discussion, please meet us as the poster. Thank you.